Dear students, Namaste and welcome back to a new mathematics session. In today's session, we shall discuss a very important concept in probability, that is Bayes' theorem and its applications. Let's move on to the topic. Before discussing Bayes' theorem, let's discuss partition of a sample space. Consider a sample space S. It is subdivided into different events E1, E2, E3, etc. En, and simply you cannot partition S as E1, E2, E3, etc. These E1, E2, E3, these events should follow some criteria. A set of events E1, E2, etc. En is said to represent a partition of sample space S if the first condition is EI intersection EJ equal to phi. In the sense, these events should be disjoint sets. Means if you take the intersection, it should be a null set. Simply if you say there should not be any common portion when we consider two events. And I not equal to j. In the sense E1 intersection E1 you cannot take. And I comma j equal to 1, 2, 3, etc. n. This is the first condition. Means EI intersection EJ equal to null set. There should not be any common element. Second condition is E1 union, E2 union, etc. union, En is equal to S. Means if you take the union of these events, you should get the sample space. That is the second condition. Third and final condition is P of EI greater than 0. When you take the individual probabilities, it should be greater than 0. For all I is equal to 1, 2, 3, etc. n. Means if you generalize, the events E1, E2, etc. En represent a partition of sample space S if they are pairwise disjoint. Pairwise disjoint means the first one, there should not be any common element. Intersection should be a null set. Exhaustive, in the sense when you take the union of these partitions, you should get the sample space. And have a non-zero probabilities, means P of EI, means individual probabilities should be greater than 0. This is the partition of sample space. Next, theorem of total probability. Consider a sample space S and it is subdivided into E1, E2, E3, etc. En. There are different events and we have taken another event A and this A is the subset of S. Once again, consider a sample space S and it is subdivided into E1, E2, E3, etc. En different events and we have considered one more event A. A is a subset of S. And here you can see the common portion. E1 intersection A is here, E2 intersection A is here. Here also in common portion is there. Here it is En intersection A also there. So the common portions are there between A and the events E. Given that E1, E2, etc. En is a partition of sample space S, it is a partition of sample space. E1, E2, etc. En can be called as the partition of sample space S because these three conditions are satisfied. There is EI intersection EJ. When you consider two events E1 and E2, there is no common element. And when you consider E1, E2, etc. En, we will get a sample space S. And next, individual probabilities greater than 0. So we can say E1, E2, etc. En is a partition of sample space S. So we can write S is equal to E1 union, E2 union, etc. union, En because these E1, E2, etc. are the partition of sample space, means this condition is satisfied. Then we know that for any event A, here A is considered as a subset of S. A is inside of S. So A is equal to A intersection S, we can write. So A will be equal to A intersection F. A also can be written as the common portion between S and A. So A is equal to A intersection S. Then A intersection this S we can replace by E1 union, E2 union, etc. union, En that we have written. Next, just separate it. A intersection E1 union A intersection E2 union A intersection E3, etc. union A intersection En. Then when we take the probabilities on the left side and right side, P of A is equal to P of A intersection E1 union, A intersection E2 union, etc. union, A intersection En. just separate it, that is P of A intersection E1 plus P of A intersection E2 plus P etc plus P of A intersection En. So this one we have already learned, that is the multiplication rule of probability. P of A intersection E1 is equal to P of E1 into P of A given E1, or if you generalize, P of A intersection EI is equal to P of EI into P of A given EI, P of EI into P of A given EI. That is what we have learned in multiplication rule of probability. So when we substitute it, P of A is equal to this P of A intersection E1 will change as P of E1 into P of A given E1 plus next is P of E2 into P of A given E2 plus etc plus P of En into P of A given En. So these individual cases we will consider and we will use the multiplication theorem of probability. That is, in general we can say P of A is equal to sigma. Sigma means summation, sum of P of Ej into P of A given Ej. I you cannot take because here generally we have taken as I. So you can use J, the letter. P of A is equal to sigma J is equal to 1 to n P of Ej into P of A given Ej. This is the theorem of total probability. Next, we shall discuss the Bayes theorem. Consider that there are two bags, bag 1 and bag 2. Two bags are there with us. Bag 1 contains 2 white and 3 red balls. There are 2 white and 3 red balls are there in bag 1. And bag 2 contains 4 white and 5 red balls. So 4 white and 5 red balls are there in bag 2. Here, we know how to find out the probability of selecting any one of the bags. There are 2 bags are there. Probability of choosing any one of the bags out of these 2 bags is 1 by 2. Next is, we have already learned in conditional probability. We know how to find the probability of choosing a white ball given that it is from bag 1. Probability of choosing a white ball given that it should be from bag 1. This is conditional probability. Given condition is there. Bag already one thing is happened. You have already selected bag 1. And what is the probability of choosing a white ball from that? So this is a conditional probability we have learned in this chapter itself. Now just think of another scenario. One ball is drawn at random from one of the bags and it is found to be white. You have taken one ball and you have got the result as white ball. Find the probability that it was from bag 1. So we have to find out the probability of that ball as from bag 1. Here the previous case, when you check, we can find the probability of choosing a white ball. You are choosing a white ball given that the condition is already given, means this thing is already happened. It is from bag 1. You have selected the bag already, and from that bag what is the probability of choosing a white ball? That is the conditional probability we have learned. And here the new situation or new scenario is, you are choosing a ball at random from any one of the bags, and after choosing, when you check the ball, it is a white ball. And here we are asked to find out, or we have to think of the probability of that ball from bag 1. So find the probability that it was from bag 1. So it is just a reverse process of the previous condition or previous conditional probability. Here we have to find the reverse probability of bag 1 to be selected when an event occurred after it is known. So here we have to find the reverse probability of bag 1 to be selected when an event occurred after it is known. When an event occurred in the sense, you are choosing a ball from any one of the bags and you have checked that ball, it is white. So we have to find out the probability of getting this white ball from bag 1. Famous mathematician John Bayes solved the problem of finding reverse probability by using conditional probability. The formula developed by him is known as the Bayes theorem. So this is the Bayes theorem. This is the situation for Bayes theorem, and it is very important to identify in the examination which way we have to solve the question, whether it is conditional probability we have to use or whether we have to use the Bayes theorem. Next we shall discuss the Bayes theorem formula. if E1, E2, etc. En are n non-empty events which constitute a partition of sample space S, that is, partition of sample space means these E1, E2, etc. En need to follow some conditions. That is, this should be pairwise disjoint, means when you take the intersection, it should be a null set. E1 intersection E2 or any two events intersection, if you take, it should be a null set, means there should not be a common element. And when you take the union, E1 union, E2 union, etc. union En, it should be a sample space. You should get the sample space. And one more thing we have learned in the partition of sample space, these E1, E2, etc. should have a non-zero probability greater than 0. And A is any event of non-zero probability, then P of EI given A, P of EI given A in the sense here E is the partition of sample space and A is any event which is having a non-zero probability, that is equal to P of EI into P of A given EI divided by sigma j is equal to 1 to n P of EJ into P of A given EJ. Here in the denominator we are using j because I we have already used in the numerator. So P of EI given A is equal to P of EI into P of A given EI divided by sigma j is equal to 1 to n P of EJ into P of A given EJ. Remember this here in the first part it should be an event P of E given A in the sense an event which is having a non-zero probability for any I is equal to 1, 2, 3, etc. n. So here let's discuss how this formula has derived, not in the examination point of view but for understanding purpose it is very useful for you. By formula of conditional probability we have learned P of EI given A. This one by using conditional probability we can write P of A intersection EI divided by P of A. So P of EI given A we can write by using the conditional probability, that is P of A intersection EI divided by P of A. Conditional probability we have learned P of A given B is equal to P of A intersection B divided by P of B. So by using that conditional probability we have written the formula. Then this multiplication theorem we can use and change this part. By multiplication rule of probability, P of A intersection EI is equal to P of EI into P of A given EI. So just a substitute here, that is P of EI into P of A given EI divided by P of A. And this P of A also we can change by using the total probability formula we have learned in the previous slide. So by using the theorem of total probability, P of A we can write it as sigma j is equal to 1 to n P of EJ into P of A given EJ. Just a substitute by replacing P of A, that is P of EI into P of A given EI. In the numerator it is same, denominator P of A will change by using total probability formula, that is sigma j is equal to 1 to n P of EJ into P of A given EJ. So this is the Bayes theorem formula. Next we shall discuss the exercise questions. Exercise 13.3, question number 1. An urn contains 5 red and 5 black balls. A ball is drawn at random, its color is noted and is returned to the urn. Moreover, 2 additional balls of the color drawn are put in the urn and then a ball is drawn at random. What is the probability that the second ball is red? Let's go through the question again. An urn contains 5 red and 5 black balls, total 10 balls, 5 red ball and 5 black balls. And you are choosing a ball at random and its color is noted. You are choosing a ball and the color is noted and then you are keeping it back the ball. And which color you have noted, the same color, 2 more balls you are adding to the urn. Then you are taking the second ball. 1 more ball you are taking. And we have to find out the probability that the second ball is red. Once again, a bag contains 5 red and 5 black balls, total 10 balls. You are choosing 1 ball at random. You may get red or black, whatever it is, you are noting the color and keeping it back the ball. And then which color you have noted, the same color, 2 more balls you are adding to the urn. And you are choosing 1 more ball. And we have to find out the probability that the second ball is red. So total 5 plus 5, 10 balls, 5 red and 5 black balls. Here the second ball should be red the second ball, by keeping the second ball constant, means fixing the second ball as red, we have two options. First one is black, second ball is red. One more option is both also red. First one is red, second one also red. These are the two options. Second ball should be red, so we are fixing second ball as red. There are two options. First one is black, first one is red. So probability that first ball is black. First ball black means we have 5 black balls. So 5 divided by 10 total, 1 by 2. Now you have taken a black ball, so you are keeping it back and you are adding 2 more black balls because you have taken first black. So now you have 5 red and 5 plus 2, 7 black balls. You have added 2 more black balls here. Now probability of choosing a red ball. Probability of choosing a red ball when the first ball is black is equal to, you have taken the first ball, black ball, and next you are choosing a red ball. So total here 5 red balls are there, here 5 red balls are there, 7 black balls are there. So we are going to choose a red ball. So 5 divided by total, now 5 plus 7, 12. So 5 divided by 12 is the probability. And in the second case, first one is a red. Probability of choosing a red ball is 5 divided by 10, 1 by 2. Now first ball you have taken as red, you have noted the color and you are keeping it back the ball to the urn, and then you are adding 2 more red balls. So now you have 5 plus 2, 7 red balls and 5 black balls. Now you are going to choose a red ball again. Probability of second ball is red when the first ball is red is, here we have red is 7, 5 plus 2, 7. You have already taken a red ball, because of that you have added 2 red balls again. So 5 plus 2, 7 red balls, total 12. 7 divided by 12 is the probability. Now probability that the second ball is red is equal to probability of BR plus probability of RR. These two probabilities we have to add. That is equal to probability of getting a black ball, that is 1 by 2. Probability of getting a red ball in the second time, that is 5 by 12. So 1 by 2 into 5 by 12 plus probability of getting a red ball in the first time, that is 1 by 2 into probability of getting a second ball red when the first ball is red, that is 7 divided by 12. Just go for simplification. 1 into 5, that is 5, 2 into 12, that is 24, 1 into 7 is 7, 2 into 12, 24. That is equal to 5 plus 7 is 12, common denominator. So 12 divided by 24, that is equal to 1 by 2. So the required probability is 1 by 2. Next, we shall discuss question number 2. A bag contains 4 red and 4 black balls. Another bag contains 2 red and 6 black balls. One of the 2 bags is selected at random and a ball is drawn from the bag which is found to be red. Find the probability that the ball is drawn from the first bag. Quite clear, it is a reverse probability, because we are asked to find out the probability of choosing that red ball from the first bag. So there are 2 bags. First bag is having 4 red and 4 black balls, and the second bag is having 2 red and 6 black balls. And you are choosing one of the bags at random and a ball is taking from it, and it is found to be red, means you are choosing a red ball, and we have to find out the probability that the chosen red ball is from first bag. So here there are 2 bags. Bag 1 is having 4 red and 4 black balls, and bag 2 is having 2 red and 6 black balls. Let's define the events E1 and E2. Here E1 and E2 be the events of selecting first bag and second bag respectively. So E1 and E2 be the events of selecting first bag and second bag respectively, and P of E1 and P of E2 are same. Probability of choosing a bag out of these 2 bags, that is 1 by 2. Probability of choosing one bag out of these 2 bags, that is 1 by 2. Simple probability, that is. Next is, let A be the event of getting a red ball. Another event we have assumed, that is our experiment drawing a red ball. So let A be the event of getting a red ball. And conditional probabilities we are calculating now. Probability of A given E1, meaning is probability of getting a red ball given that it is from bag 1. So from bag 1 getting a red ball. So 4 red balls are there in bag 1, total 8 balls. 4 divided by 8, that is equal to 1 divided by 2. Next is probability of A given E2. That is probability of choosing a red ball given that red ball is from bag 2, second bag. In bag 2 there are 2 red balls, total 8 balls. That is equal to 2 divided by 8, that is equal to 1 divided by 4. You can cancel 2 and 8, 1 by 4. What we have to calculate, that is the question. Now we have to calculate the probability that the ball is drawn from the first bag, means E1. So probability of E1 given A we have to find out. Probability of E1 in the sense choosing first ball given that the taken ball is red A, even getting a red ball. So probability of E1 given A we have to calculate. By using Bayes theorem, we can write probability of E1 given A is equal to probability of E1 into probability of A given E1 divided by sum of the other probabilities, that is P of E1 into P of A given E1 plus here there are two events E1 and E2, that means P of E2 into P of A given E2. All the calculations we have done here, that is equal to P of E1, that is 1 by 2, P of A given E1 we have calculated, that also 1 by 2 divided by P of E1 into P of A given E1, the same quantity 1 by 2 into 1 by 2 plus P of E2, that is 1 by 2 into P of A given E2. A given E2 is 1 by 4. Little bit of calculation, that is 1 into 1, 1, 2 into 2, 4. So 1 by 4. Here also 1 by 4 plus 1 by 8. 1 by 5. 1 by 4 plus 1 by 8. That is equal to 1 by 4 divided by here 8. If you take LCM, here 2 will be coming. 2 plus 1, 3. So 3 by 8. That is equal to here 4 and 8 we can cancel 2 times. Denominator will come the numerator. So 2 divided by 3 is the required probability. Next we shall discuss question number 3. Of the students in a college, it is known that 60% reside in hostel and 40% are day scholars, means not residing in hostel. Previous year results report that 30% of all the students who reside in hostel attain A grade and 20% of the day scholars attain A grade in their annual examination. At the end of the year, one student is chosen at random from the college and he has an A grade. What is the probability that the student is hosteler? Here there are two categories it is mentioned, hostelers and day scholars. 60% are hostelers and 40% are day scholars. These two we can take it as E1 and E2. Previous year results report that 30% of students who reside in hostel attain A grade. Means this is we can consider as an event A, student who attain A grade. Then 20% of the day scholars attain A grade in their annual examination. So up to here when we read, we can define E1 means hostler, E2 day scholars, and A we can consider as student who attain A grade. And we have to find out if a student is chosen at random who is having an A grade, we have to find out the probability that the student is a hosteler. Means surely it is a reverse probability. Using Bayes theorem, we have to calculate the answer, required probability. As before, let's define E1 and E2. Let E1 and E2 be the events that the student is a hosteler and a day scholar respectively, and A be the event that the chosen student gets grade A or A grade. This we have already discussed. Then P of E1, it is given to you here 60% reside in hostel. So 60 by 100, that is equal to 0.6. Then P of E2 is 40% of day scholars, that is 40 by 100, that is equal to 0.4. Then next is probability of student getting an A grade is a hosteler. Means P of A given E1, student who is getting an A grade given that he or she is a hosteler. That is 30%, that is 30 by 100, 0.3. Next is probability of student getting an A grade is a day scholar. That is P of A given E2, means probability of getting a student A grade student given that he or she is from a day scholars list. So P of A given E2. It is given to you here 20%. That is 20 by 100, 0.2. What we have to calculate is we need to find the P of E1 given A. Means we have to find out if a student is chosen at random from the college and he or she has an A grade, what is the probability that the student is a hosteler? Means given that he or she is having an A grade, and we have to find out the probability that he or she is a hosteler. So P of E1 given A. Condition is given to you, that is he or she is having an A grade. Given that he or she is having an A grade, we have to find out the probability that he or she is a hosteler. So P of E1 given A, by using Bayes theorem, we can say P of E1 given A is equal to P of E1 into P of A given E1 divided by the total probability. That is P of E1 into P of A given E1 plus 2 events are there. E2 also is there. So P of E2 into P of A given E2. Let's substitute the values. P of E1 is 0.6 and P of A given E1, that is 0.3. Then again P of E1 into P of A given E1, that is 0.6 into 0.3 plus P of E2. P of E2 is 0.4 into P of A given E2. A given E2 is 0.2. Just multiply it. 0.6 into 0.3 is 0.18. Then here 0.18 plus 0.08, that is 0.26. That is equal to 18 divided by 26. Just we have to multiply 100 numerator and denominator. 18 by 26 will come. When we cancel the common term 2, that is 9 divided by 13. So the required probability is 9 by 13. Move on to question number 4. In answering a question on a multiple choice test, a student either knows the answer or guesses. Let 3 by 4 be the probability that he knows the answer and 1 by 4 be the probability that he guesses. Assuming that a student who guesses that the answer will be correct with probability 1 by 4, what is the probability that the student knows the answer given that he answered correctly? Let's go through the question. While answering a multiple choice question, the student is having two approaches. Either he knows the answer. If he knows the answer, he will directly tell. If you don't know the answer, he will go for guessing. So there are two options. Means two events we can say, E1 and E2. E1 is knows the answer, E2 guesses. And probability is also given to you. The probability that he knows the answer is 3 by 4. So P of E1 is 3 by 4. And 1 by 4 be the probability that he guesses. So P of E2 is 1 by 4. And assuming that a student who guesses at the answer will be correct with a probability 1 by 4. If we guess the answer and the probability of answer is correct is 1 by 4. And here one more thing we have to derive that is not given to you here. If he knows the answer, the probability that the answer is correct is 1. It is a sure probability because he knows the answer. If he knows the answer, the probability of that answer is correct is 1. It is a sure probability. Here what we have to calculate is we have to find out the probability that the student knows the answer given that he answered it correctly. So reverse probability it is. This one we can take it as A, means student answered correctly. That is given one, and we have to find out the probability that the student knows the answer. Student knows the answer, it is an event. So maybe A given E1 given A we have to calculate because E1 is this one, student knows the answer, already we have taken. E1 given A, this one we have already assumed as A. Student answered correctly. So let's define all these things. Let E1 student know the answer from here. Next is E2 student who guesses. The next is A we can define, that is student answers correctly. And P of E1 it is given to you in the question 3 by 4, and P of E2 that is given to you 1 by 4. And from here onwards you have to be careful while writing. The probability that the student answered correctly given that he knows the answer. As I said before, it is not mentioned here, but we have to write. If the student knows the answer and the probability of that answer is correct is 1. It is a sure probability. Here it is quite clear. A given E1. A in the sense the student answer is correct. Student answered correctly. Given that means already happened. He knows the answer. This is already happened one. Student knows the answer. So probability of A given E1 is 1. Conditional probability writing time, you have to be careful. Next one, probability that the student answered correctly given that he guessed. That is, here it is 1 by 4. So P of A given E2. A given E2 in the sense P of A is here. Student answered correctly. Already happened one, that is E2. E2 is he guessed. E2 is he guessed. Student guesses is E2 is 1 by 4. So all the requirements we have written. P of E1 is written, P of E2 is written, P of A given E1 is written, P of A given E2 is written. So what we have to calculate is P of E1 given A. Means what is the probability that the student knows the answer. Knows the answer in the sense here E1. So P of E1 given that he answered correctly means P of E1 given answered correctly is A. So P of E1 given A we have to calculate by using Bayes theorem. P of E1 given A is equal to P of E1 into P of A given E1 divided by P of E1 into P of A given E1 plus P of E2 into P of A given E2 because two events are there. Let's substitute it. P of E1 is 3 by 4 into P of A given E1. P of A given E1 is 1. So this is not given to you in the question. We have to write it. Divided by P of E1 into P of A given E1, same as in the numerator, 3 by 4 into 1 plus P of E2. P of E2 is 1 by 4. 1 by 4 into P of A given E2. A given E2 is again 1 by 4. That is equal to 3 by 4 into 1 is 3 by 4. Then 3 by 4 into 1 again 3 by 4. 1 into 1 1. 4 into 4 16. So 1 by 16. That is equal to 3 by 4 divided by 16 if you take as LCM. Here 4 will be coming. 4 into 3 12. 12 plus 1 is 13. So 13 by 16. When you go for calculation, 3 by 4 into reciprocally you have to multiply 16 by 13. That is 4 and 16 we can cancel 4 times. 4 into 3 12. 12 divided by 13 is the required probability. Next we shall discuss question number 5. The question is, a laboratory blood test is 99% effective in detecting a certain disease when it is in fact present. However, the test also yields a false positive result for 0.5% of the healthy person tested. That is, if a healthy person is tested, then the probability 0.005, the test will imply he has the disease. If 0.1% of the population actually has the disease, what is the probability that a person has the disease given that his test result is positive? Here, this is the real application of Bayes theorem. You have to read very carefully and define E1, E2 and A and all. So, a laboratory blood test is 99% effective in detecting a certain disease when it is in fact present. So, it is 99% effective in the sense if a person is having the disease through test it will detect and it is effective means 99% it will be successful. Means a person is having disease it will detect 99%. However, the test also yield a false positive result for 0.5% of the healthy person tested. Means sometimes if a healthy person means a person who is not having the disease testing time also it may show positive result, that probability is 0.5%. Means a person who is not having disease will show the test is positive, the probability is 0.5%. Here it is mentioned those things. That is, if a healthy person is tested, then with the probability 0.005, that is this one, 0.5%. The test will imply he has the disease. If 0.1% of the population actually has the disease, so in a particular number of people means that is called the population. But in a particular number of people, actually 0.1% will have the 0.1% of population actually will have the disease. Here You have to find out what is the probability that a person has a disease given that his test result is positive. You have to find out the probability that a person has the disease and the given condition is his test result also positive. So here let's define E1, E2 and A. E1 means a person has the disease, and E2 a person does not have the disease. And here it is given to you 0.1% of the population actually has the disease. And A is, here it is, the test result is positive. Let A be the event that the blood test result is positive. And let's write P of E1. P of E1 is, here it is given. Unlike the previous questions, this is the last statement it is given. 0.1% of the population actually has the disease. Means probability that a person has the disease is 0.1%. That is 0.1 by 100. That is 0.001. Next is P of E2. P of E2 is person does not have the disease. That is not here. It is already mentioned here. A person who is having disease, the person has the disease is 0.001. Person who does not have the disease is 1 minus of P of E1. That is 1 minus of 0.001. That is 0.999. Next, probability of result is positive given that the person has the disease. That is P of A given E1. A is result is positive given one is E1. E1 means a person has the disease. That is equal to 99%. Means probability of result is positive given that the person is having the disease. That is given to you 99% is effective. 99% effective in the sense a person is having disease will be detected positive. So that is P of A given E1, that is 99%, that is 0.99. Next is probability of result is positive given that the person has no disease. That is faulty. A given E2. Probability of result is positive. That is A. Given that the person has no disease. That is E2. So P of A given E2 is 0.5%. That is 0.005. So probability that the person has a disease given that his test result is positive. Test result is positive in the sense that is here A. So that is given condition, given A. Probability that a person has the disease, that is E1. So E1 given A is equal to, by using Bayes theorem we can write P of E1 into P of A given E1 divided by P of E1 into P of A given E1 plus P of E2 into P of A given E2. Let's substitute it. P of E1 we have got a 0.001 into P of A given E1. A given E1 is 0.99 divided by 0.001 into 0.99 plus P of E2. P of E2 we have calculated 0.999 into P of A given E2. A given E2 is here 0.005. Here all decimal calculations you have to be very careful when you calculate. That is equal to, when you multiply these two, 99 into 1 is 99. Here after the decimal 3 digit, here 2 digits. So total 5 digits. 1, 2, 3, 4, 5 digits. Let's adjust adjustment only here. Here when you multiply, just like the previous one, the same thing. 99 into 1 we can write as 99. Then after the decimal 5 digits. Just add zeros. Plus 999 into 5, that is 4995. Here after the decimal 3 digit, here 3 digits. So total 6 digits. We have only 4 digits. So 2 more zeros you have to put on the left side. That is 0.004995. That is equal to 0.00099 divided by, when you add these two, we will get it as 0.005985. Please do the calculation carefully on the right side of your notebook. Please do not copy. That is equal to, just here denominator 1, 2, 3, 4, 5, 6. Numerator 1, 2, 3, 4, 5. After the decimal, here 6 places. Here after the decimal 5 places. So 6 is bigger. Just to multiply 1 after 6 zeros in the numerator and denominator, so that the decimal portion will be eliminated. So just multiplied numerator and denominator, it becomes 990 divided by 5985. So that is equal to 110 divided by 5985 means here we have cancelled 11. By using 11 we have cancelled. Again here again common factor is there here, that is 22 by 133 means we have cancelled again 5. So 22 by 133 is the required probability. So you have to go through the entire conditions once again and try to do it in a separate sheet of paper, this one. Dear students, today we have discussed Bayes theorem and we have solved first 5 questions from exercise 13.3. I request all the students to go through these questions and solve these questions independently in a sheet of paper. While solving, if you have any doubt, please note it and keep. We will discuss it during the discussion session. Thank you for watching.